so that I don't forget. Okay, and so, yeah, I wanted to start with a review of some of the things we covered last time before we go on to new things. But first of all, are there any questions or comments? Okay, so let's get started. So last time we discussed this lemma. So I didn't prove this lemma, but we'll use some of these results. So they're just about sort of topological properties of algebraic groups. So if we have two open dense subsets, then together they generate, then their products UV, products of elements in U and elements in V give you all of G. And then if you have a subgroup, then its closure is also a subgroup. Another related property is that if a subgroup contains an open subset of its closure, then it's closed. And then if we have a morphism of algebraic groups, then the kernel is a closed and normal subgroup of G, and the image is a closed subgroup of G prime. And the connected component of the identity of G is equal to the connected component of the image of G. Okay, so we mentioned this, and then we gave the definition of a G variety or G space. So it's just an algebraic variety with an action of G, and this action is given by a morphism of variety, so it's compatible with the algebraic structure. And we can say it in terms of diagrams. So this diagram commutes and this diagram commutes. This diagram just says that we can, if we have two elements of G, we can either act on X one at a time or multiply them together and then act by X. And this just says that the identity of G acts as the identity automorphism of X. And there's a notion of an equivariant map between G spaces. So this is the diagram definition. You can translate this into a sort of an equation definition. And we had the notion of the orbit of an element in a G space and the stabilizer or isotropy group, which is a closed subgroup of G that stabilizes that point. And a homogeneous G variety is one where G acts transitively. And we had these actions, so the conjugation action of G on itself, the action of G on itself by left translations and by right translations. We have a G inverse here. Okay, there's the notion of a principal homogeneous space where the action is transitive, so it's a homogeneous space, but all stabilizers are trivial. And these left and right translation actions are examples of principal homogeneous spaces. Then we had the notion of a representation of a algebraic group. And so this is like a G space, but the action is linear. So every element in G acts by a linear automorphism. So something in the general linear group. So in other words, representation of G is a homomorphism of algebraic groups from G to the general linear group of the vector space. Yeah, we can choose a basis so that we get this homomorphism as mapping from G to GLN. Okay, so then we were moving towards proving the embedding theorem, so that any linear algebraic group is a closed subgroup of the general linear group for some n. So first kind of observation, I guess this is not super necessary, but it's kind of in the spirit of things, that any finite group is a linear algebraic group. And we see this by embedding G into the general linear group for the group algebra of G. And yeah, so that, and since this is a linear algebraic group and we have a closed embedding of G inside there, that means G is a linear algebraic group. All right. And yeah, the group algebra of G is related to the affine algebra associated to V as an algebraic variety by a certain duality. So there's a Hopf duality going on here. Okay, and then we talked about this theorem, the embedding theorem. And yeah, the idea is to kind of mimic in some sense what happened in the finite group setting, but of course it will be more sophisticated when the group is not finite. So one very important thing is this action of G on its affine algebra. So this is coming from the right multiplication action of G on itself. So this is the formula. So a function goes to the function that first takes x, then acts by G on the right, and then you apply f. And so we sort of examined the affine algebra of G as a representation of G. It's an infinite dimensional representation, but we can still examine it as a representation. And we had this somewhat technical lemma with two parts, and it just comes down to, so I'll scroll down here, it comes down to understanding this sort of computation. So as long as you can internalize this, what's going on here, and internalize this computation, then the lemma is pretty easy, but maybe it looks kind of bizarre at first. Right, so that was the lemma. And then so part two, and then the proof of the embedding theorem starts out with taking some generators for the affine algebra as an algebra. So it's an infinite dimensional vector space, but it's finitely generated as an algebra. We can take a set of generators, and we can, by the lemma, we can extend the space spanned by the set of generators to something that's invariant under this rho G action for every G. And using that, we basically, so we get an action of G on this space W. So W is something that contains a generating set. So it's a finite dimensional subspace of affine algebra of G that contains a generating set. And it's also invariant under all these rho Gs. And yeah, and that's the embedding. So yeah, there's things to check that I didn't talk about in detail, but that's the embedding. And it's not unique, but we have an embedding. Okay, there was an extension of this embedding, and there's also, so these ideas about thinking about the affine algebra of G as a G space, as a representation of G, some of those ideas extend to thinking about the affine algebra of any affine G variety as a representation of G. So this is how we think about it as a representation of G. Again, it's finite dimensional in general. Yeah, there's some, so with this representation, this evaluation map is equivariant or invariant, since G acts trivially on the ground field. And we had this generalization of the lemma previously, and the upshot is that anytime we have a G variety, if we look at its affine algebra, it's infinite dimensional, but it's somehow, but it's the direct sum, or not the direct sum, but it's the union of finite dimensional representations of G. So even though it's infinite dimensional, it's every piece of it, every element lives in some finite dimensional representation. All right. Yeah, so this was sort of the themes in what I've summarized so far are the embedding theorem, and also thinking about representations and going from a G variety to its affine algebra, which is a representation of G. And the other thing we talked about is that yeah, this result that any morphism of algebraic groups from GM to GM is given by just raising everything to some power and some integer power. So yeah, and we talked about the proof of that. So it's pretty algebraic. It comes down to showing that the units of the algebra of Laurent polynomials, so polynomials in T inverse, the units of that algebra are just given by monomials in T with some non-zero coefficient. And so each of these, and then we showed that each of these defines a morphism of algebraic groups, except that we need lambda to be equal to 1. So we use this co-unit axiom here to argue that lambda has to be equal to 1. So the upshot is that these are, so that proves this result, that all the group homomorphisms from GM, from the multiplicative group to itself, are given just by raising things to some integer power. So in other words, they're identified with Z. And in fact, this is as groups. So the only invertible maps from GM to itself are the identity and taking the inverse. And just like the only invertible elements in the group of integers are 1 and -1. Okay, so, oh, maybe that's not right. Okay, yeah, scratch that. Okay, so that was this set of notes. So any questions on this before I move on to the PDF about the Jordan decomposition?
Yes, just
Sure.
say the group homomorphisms are given by this by. You mean that all group homomorphism or just algebraic group homomorphisms?
Well, definitely algebraic group homomorphisms in terms of, I imagine if you don't take into account the algebraic variety structure, I guess there might be more, but I get for our purposes, we're only going to be concerned with algebraic group homomorphisms. Okay, so great. So let me move to the other PDF. Where is it?
So real quick,
Sure.
the property writing K of X as a union of rational representations, does that basically show that any algebraic group has a semi-simple representation?
So semi-simple means that it would have to break up as a direct sum decomposition. And this union, this fact about the affine algebra of any G variety is there's no direct sum decomposition there, it's just a union. Does that answer your question?
Yeah.
Okay, great. So let's see here. Okay, so last time again, we started talking about the Jordan decomposition. So, okay, so first some basic definitions. So if we have a vector space of dimension n, then an endomorphism is said to be diagonalizable or semi-simple if we can find a basis for V consisting of eigenvectors for this endomorphism. So in other words, in that basis, G will just be a diagonal matrix. The endomorphism is nilpotent if some power of it is 0. And this is equivalent to saying that all the eigenvalues are equal to 0. It's unipotent if G minus the identity is nilpotent. So that means all the eigenvalues are equal to 1. So these are kind of extreme cases, these different things. In particular, something is semi-simple and nilpotent if and only if it's equal to 0. And it's semi-simple and unipotent if and only if it's equal to the identity. And you should think of these examples, so if we fix a basis, so we fix an isomorphism with k to the n, then endomorphisms are just given by matrices, and any diagonal matrix is semi-simple, and any matrix of this form, so upper triangular with ones along the diagonal, that's unipotent. And any matrix that has that's upper triangular but with zeros along the diagonal, so sometimes this is called strictly upper triangular, this is nilpotent. Any such matrix is nilpotent. So these are kind of the canonical examples of such endomorphisms. Okay, and like we said before, a Jordan block is a square matrix of this form, so lambdas along the diagonals for some lambda in the field, ones along the superdiagonal, zeros elsewhere. So yeah, so a Jordan block has a single eigenvalue, lambda of multiplicity equal to the dimension. Yeah, if we subtract out lambda times identity, then we get something that's nilpotent, because then we just get something with ones along the superdiagonal. As we take powers, those ones move towards the right, top right corner, and then so eventually we get something zero. All right, and yeah, so for a Jordan block, we can write down these decompositions, so we can separate it out into the semi-simple part and the nilpotent part. So the semi-simple part is just a diagonal matrix, so it commutes with everything. In particular, it commutes with the nilpotent part. We can also arrange it so that it's the product. So as long as lambda is non-zero, we can arrange it so that the Jordan block is the product of something semi-simple with something unipotent. And again, the semi-simple part in this case will just be scalar, scalar times identity, so it commutes with everything. In particular, it commutes with the unipotent part. And this can be generalized. So first, the Jordan decomposition, which you've probably seen before, we can take any endomorphism and we can find some basis for which this endomorphism is written as a matrix is just a block diagonal matrix with each block given by a Jordan block. So a given eigenvalue can appear, so first of all, the eigenvalues of G are just the diagonal matrices, so all the lambdas across all the Jordan blocks. A given lambda can appear in more than one Jordan block, but each Jordan block has one single lambda. And yeah, okay. So kind of putting these things together, so these are all things that I guess are proven in a previous course, assumed knowledge, a prerequisite, but now to sort of formulate it in the language that we need for this course, we have this lemma that says that for any endomorphism, there's a semi-simple element and a nilpotent element, such that G is the sum of these two, and these two commute. And the proof of the lemma is just thinking about the Jordan decomposition and applying those observations. And if we think about it, the eigenvalues of G counted with multiplicity coincide with eigenvalues of the semi-simple part. So the semi-simple part knows everything about the eigenvalues of G. And then I think, yeah, so then I started giving the proof of this proposition. So this proposition says several things. So if we have this Jordan decomposition of an endomorphism into a semi-simple part and a nilpotent part, first of all, these elements GS and GN are given in terms of polynomials, given in terms of G as a polynomial. So there's a polynomial that when we plug in G and evaluate it inside the endomorphism algebra of V, we get GS, and similarly for a different polynomial, we get GN. And yeah, I'll say a bit more about what this means. And these two elements are uniquely determined, satisfying the conditions of the lemma. And also this Jordan decomposition is compatible with taking subspaces that are stable for this endomorphism. Also quotients, I'll mention that later on. So in other words, the semi-simple part of the restriction of G to a G-stable subspace is equal to the restriction of the G-stable sorry, the semi-simple part of G, and similarly for the nilpotent part. Okay, so how does the proof go? Well, we need a bunch of stuff. So first of all, we need the characteristic polynomial of G. So you'll remember, so by definition, this is the determinant of T minus G. And you remember that the eigenvalues are the roots of the characteristic polynomial. So they may occur with multiplicity. So if we take lambda 1 through lambda r to be the distinct eigenvalues of G, then the characteristic polynomial is just this product, T minus lambda I to the ni being the multiplicity. And yeah, we think of this as a polynomial in K brackets T. We also, for every lambda, for every distinct eigenvalue, we have the generalized eigenspace of lambda I. So yeah, so the eigenspace would be if we took G minus lambda I, V is equal to 0. So if we didn't have a power here, but to get the generalized eigenspace, we take this power. And V breaks up as a direct sum of its generalized eigenspaces. So we also had this fact, the Chinese remainder theorem, that says that this quotient splits up as a direct sum of rings, and each ring is the quotient by T minus lambda I to the ni. So now what we do is we take, so to construct this P, so we're aiming to find this polynomial P that gives the semi-simple part. So the semi-simple part on each VI is just lambda times the identity. So we'll see that, we'll see that later on, but that kind of motivates why we do the following. So we take inside this direct sum of rings, inside the ith piece, we take just the constant polynomial lambda I. And by this isomorphism, there exists a polynomial here that is congruent to this constant polynomial lambda I mod T minus lambda I to the ni. Okay, so this isomorphism allows us to do this. And now the claim, okay, so first this...
Can you repeat that sentence or just stay on that?
Yeah, sure. So the claim, so, okay, so first of all, we have this isomorphism of rings. And once we have this isomorphism, we want to take something in here that's kind of defined by a condition in here. So on this side, we take in the ith factor, we just take the constant polynomial lambda I in the ith factor. So lambda I lives in K brackets T, but we mod out, so we get something in here in the ith factor, and we have R different factors. And by this isomorphism, there is something, there is a polynomial in here that we call P of T that maps to that element that we've chosen, lambda I in the ith factor. So we just take that polynomial P of T, and it's only really well defined up to phi, as we'll see later on, but we can still choose some concrete P of T. Does that make sense?
Yeah, thanks.
Okay, great. Thanks for the question. So we argued last time that P of T can be chosen so that P of 0 is equal to 0. And this is just because P is only really well defined up to phi. So we can, if necessary, if it's not already equal to 0, we can subtract a multiple of phi to make it equal to 0. And it'll still have the property about the lambdas. Okay, so the claim is that that P of G is equal to GS. So first of all, what do we mean by this statement? What do we mean by having a polynomial, plugging in G and getting out some other endomorphism? Well, so the way, I guess there's different ways to think about it, but the way that kind of makes most sense to me is the following. So we have this algebra homomorphism from polynomial algebra in one variable to the endomorphism algebra of V. And this is kind of silly, that just takes T to G. It just picks out this element G. And now if we have a polynomial in here, then P, so let's call it P of T, then by P of G, we mean the image of this polynomial inside the endomorphism algebra. So we just plug in G and we multiply out and expand, multiply by scalars, add, subtract, expand it all out. We get a new endomorphism, and that's what we call P of G. And the reason why it's okay to just work modulo the characteristic polynomial is because G satisfies its own characteristic polynomial. So this map rho factors through K brackets T mod the characteristic polynomial, which, as we saw on the page before, in turn breaks up as the direct sum over K brackets T mod T minus lambda I to the n I. Okay, does this picture make sense to people? All right, so how do we prove this identity here? Okay, so yeah. Okay, so first of all, the first thing to kind of observe is that each of these generalized eigenspaces is stable under G. So why is that? Well, we just trace through the definition. So we want to show that we want to take a little v inside of vi, apply G to it, and argue that it's still in vi. Vi by definition was all the things that vanish under this endomorphism, G minus lambda I. And again, it's clear to everybody, but lambda sub I is really just lambda sub I times the identity endomorphism of vi, of V. So that's what I mean, because G is an endomorphism, lambda is a scalar, so maybe it's confusing, but that's all it means, lambda times the identity. And since G commutes with any scalar and G commutes with itself, we just rearrange the factors. V is in VI, so we already know that this is 0, so there we go. Okay, so each of these VIs is stable under G. So what that means is that there's a well-defined algebra homomorphism from K brackets T to the endomorphism of algebra VI, which just sends T to the restriction to G, the restriction of G to VI. So because VI is anytime we have a subspace or vector space that's stable under G, we have this such algebra homomorphism. In particular, for each VI, we have this algebra homomorphism. And now we want to argue. So let me just peek ahead. So we want to argue that this homomorphism factors through K brackets T mod T minus lambda I to the ni. So in order to get this sort of factorization, all we need to do is show that rho I vanishes, is 0 on this element T minus lambda I to the ni. And the reason that that's true is because when we do rho I, we just get a G here, and VI by definition is all the things that vanish when we apply this endomorphism. Yeah, so that's what I wrote here. So rho sub I of this is G restricted to VI minus lambda I to the ni, but that's just the 0 endomorphism on VI by the definition of VI. Okay, so we have this factorization, and and so when having this factorization, now we just do some nice manipulations. So what we want to do is first, so we'll show that P of G is equal to GS by showing that their restrictions to VI coincide. So we'll show that P of G restricted to VI is GS restricted to VI. So first of all, what's P of G restricted to VI? Well, that's the image of P of T under this rho I. So rho I maps into the endomorphism algebra of VI. And now we had the commutative diagram from the previous page that lets us write this rho I as the composition of the quotient map followed by rho I bar. So let me scroll back real quick. So that's what this diagram is telling us. So yeah, rho I is this composition. So that's what we have here. Okay, and so now what about this pi of, pi I of P of T? There's too many P's and rows and I'm getting confused. So what's pi I of P of T? Well, pi I is the quotient by T minus lambda I to the Ni. And now we were very clever with our choice of P of T because we chose it to be equal to lambda I modulo this, this ideal generated by T minus lambda I to the Ni. So that's why we chose that, that property for P of T. So that's why we can put in a lambda I here. And what's rho bar of lambda I? Well, it's lambda I is just the constant polynomial, so it goes to the constant endomorphism on VI. And the semi-simple part restricted to VI is just lambda I times the identity, because it comes from the Jordan decomposition. So GS is the diagonal part on that piece. So it's just lambda I times identity. So this shows that they coincide on VI, but V is a direct sum decomposition of these VIs. So that proves this claim about P of G being equal to GS. Okay. Any questions about this? All right.
Can you repeat the P definition? Well, what do you want? What did you want it to prove?
We wanted to prove this fact here. P of G is equal to GS. Or are you asking about our choice of P of T?
Yeah, so this is by the Chinese reminder theorem, right?
Yeah.
Okay.
Yeah. This proof seems maybe a bit convoluted. I tried to clean it up a bit, but I don't know how successful I was. Yeah. Okay. So that's with the semi-simple part. What about the nilpotent part? Well, for the nilpotent part, it's kind of easy. We just take Q to be T minus P. So T just being the polynomial of degree 1, just T. And so why does this do what we want? Well, first of all, Q of 0 is equal to 0 because T evaluated 0 is 0 and P of 0 is 0. And Q of G is equal to Gn because Q of G is G minus GS. And we already argued that G is the sum of the semi-simple part and the nilpotent part. Okay, so this gives us these polynomials P and Q. Everybody good? All right, so, okay, so part 2. So what do we want to prove in part 2? Part 2 is a uniqueness statement. So we want to prove that this Jordan decomposition is unique. So how do we do it? Well, let's suppose it's not unique, or let's suppose there's a different decomposition. And we're going to argue that this actually turned out to be the same one we had before. So before we had G equals G sub S plus G sub N. Now let's take another one, H sub S and H sub N, such that H sub S is semi-simple, H sub N is nilpotent, and they commute and their sum is G. Okay, so we need to argue that H sub S is equal to G sub S and H sub N is equal to G sub N. So how do we do this? So first, we want to argue that G sub S minus H sub S is semi-simple. Why is this? Well, the first step is to argue that they commute. And this is where it's very useful that we got G sub S to be a polynomial in G. Because we know, Okay, so G sub S, H sub S is this polynomial G times H sub S. And now we know that G and H sub S commute. Why do they commute? Well, H sub S appears in the Jordan decomposition of G, and we know it commutes with H sub N, so it must commute with G. So since it commutes with G, it commutes with anything built out of G, any polynomial expression built out of G. So therefore it has to commute with P of G, which is equal to G of S, G sub S, and so we have that it commutes with G sub S. Okay, so that's an advantage of having G sub S being a polynomial in terms of G. All right, and now we use the standard fact. So if we have two commuting operators that are diagonalizable, then there's a basis of V consisting of simultaneous eigenvectors for those two operators. So yeah, I guess everybody's probably seen this result before. It's not too hard to prove if you haven't. In fact, I might mention a related proof that kind of proves this as well later on. So if we just take this simultaneous basis of eigenvectors, then it's also a basis of eigenvectors for the difference. So on that basis, each of these is a diagonal matrix. The difference of diagonal matrices is still diagonal, so we have what we want. All right, so that's the first. So remember, we want this uniqueness. So the second part is to prove that the difference of the nilpotent parts, so the old nilpotent part and this hypothetical new nilpotent part, that difference is nilpotent. And so why is this the case? Well, first of all, the same argument as before, but with Q instead of P, shows us that these two nilpotent pieces commute. G sub N and H sub N commute. Okay, great. So now we want to show that this difference is nilpotent. So, okay, since each of them is nilpotent, we can pick some K. K is not the ground field, it's just some integer, such that if we raise each of them to the kth power, we get something that's 0. So that's just coming from the definition of being nilpotent. But now let's take, so here I wrote the argument for the sum, but the argument is pretty much the same for the difference. You just have to include some minus signs. So if we take the sum of these and raise it to the power 2k, then we use, so the fact that they commute lets us use binomial expansion. So in general, if we just have the sum of two operators, we can't use binomial expansion as usual because they don't commute. But since they commute, we can write this out, and we can first write it out. So the powers of G to the n go from 0 to k, and then in the second part they go from k to 2k, except we factor out the k here. So yeah, so this is just, yeah, if you write it out and factor out the power of hn to the k from the first k plus 1 terms, and then you factor out a power of gn to the k from the next k term. So actually maybe this should go from j equals 1 to k. Then we get that this is a multiple of h sub k, this is a multiple of g to the k, so they must both have to be 0. And yeah, I think, let me fix this. So I think this should be sum from j equals 1 to k in the last one. Yeah. All right. Is everybody convinced that this? Okay, I gave the argument for this sum, but is everybody convinced that the sum is nilpotent? Okay, I see some thumbs up, so I'll go on. Right. Okay. So now we proved okay, so we proved that this is semi-simple, and we proved that this is nilpotent, right? So then, but now we can see that they're actually the same thing, because G sub S is really G minus G sub N. And H sub S is really H minus H sub N. So when we make those substitutions and we cancel the G's, we get that those things are the same. So we get an operator that's both semi-simple and nilpotent. And as I mentioned previously, the only such operator is the zero operator. So so both sides of this equation are equal to 0, which means that G sub S is equal to H sub S and G sub N is equal to H sub N. Okay, and that proves uniqueness. Any questions about uniqueness? All right. So, okay, so what about part 3? So part 3 is about having a G invariant, G stable subspace. So if we have a G stable subspace, that means that it's stable under any polynomial that we build out of G. So any polynomial in G will preserve this subspace. So in particular, P of G preserves it and Q of G preserves it, but that means that G sub S, the semi-simple part, and the nilpotent part both preserve W. So it's stable under those parts. So I like to think about this a bit diagrammatically. So this is kind of the diagram that's happening. So this is, up here is the algebra homomorphism we had before. T just goes to G. And since W is stable under G, we also have an algebra homomorphism rho sub W from K brackets T to endomorphism algebra of W. So this just takes T to G as an endomorphism of W. So by hypothesis, G preserves W. And these are related by the following things. So anytime we have an endomorphism of V, we can restrict it to be a linear map from W to V. And anytime we have a endomorphism of W, we can then embed W inside of V, and that gives us a linear map from W to V. And so if we do rho and then restrict to W, or if we do rho sub W and then expand this out to V, then we get the same thing. All right, hopefully that's clear and not confusing. Okay, so the upshot of this is if we have any polynomial in here, if we first do rho of it and then restrict to W, so that's the same as thinking about it as an endomorphism of W, and kind of just expanding it out to a map from W to V. So that's basically all this is saying here. So f of G restricted to W, well, that's f of G is here, restricted to W is here. That's the same as rho W of F. And then, so that's f of G restricted to W, and we can just kind of trivially think about it inside this Helm space. Okay, so why do we do this? Well, remember what we wanted to show. We wanted to show that the semi-simple part of the restriction of G to W is the same as the restriction of the restriction to W of the semi-simple part of G, and similarly for the nilpotent part. So how can we use this? Well, the semi-simple part of the restriction of G to W, well, we can use this same polynomial P of T. So there's actually a bit of an argument here to show that you can use the same, but I won't go into details. It just comes down to the fact that the characteristic polynomial of the restriction to W divides the characteristic polynomial of G itself. And so then by this observation we had up here, this is the same as rho of P of T restricted to W. That's just a semi-simple part restricted to W. And the same sort of argument works for the nilpotent part if we use Q instead of P. Okay, hopefully that makes some sense. If not, then feel free to ask. Right, so what we've shown so far is that this semi-simple and nilpotent part, semi-simple and nilpotent decomposition of an element is that we get from the Jordan decomposition. It's kind of controlled by certain polynomials, which is nice. It lets us prove various properties. It's unique, and it plays well with subspaces that are invariant under this endomorphism. And one thing I want to point out is that it also plays well with quotients. So if we had a subspace of V that's stable under the action of this endomorphism G, then there's an induced action on the quotient space. So there's a well-defined action on the quotient space, which I guess I'm calling G tilde. And we also mentioned that the semi-simple part of G preserves W. So that means there's an induced action by the semi-simple part. And similarly for the nilpotent part, there are these induced linear maps on the quotients. And so I won't spell this out, but similar arguments to what we've seen so far show that the semi-simple part of this induced map by G is exactly the map induced by the semi-simple part of G. And the nilpotent part of this map is exactly the map induced by the nilpotent part of G. So yeah, so you can think about how to kind of adapt the arguments we've seen so far to prove this, but it's not anything particularly new. All right, and now we also have this lemma. So this lemma says something about how these semi-simple nilpotent parts interact with linear maps. So if we have a linear map between two finite dimensional vector spaces, V and W, and we have an endomorphism of, I guess I put GLV, but this would be true. Yeah, I think I want this. This is true for GLV, but it's also true for NV, and I think I want NV here. So let me fix that. So if we have an endomorphism of V and an endomorphism of W, and they commute with this action in the sense that the following diagram commutes. So if we do this linear map V and then we do H, that should be the same as doing the linear map G and then the linear map phi. So this diagram commutes. Well, then we know that G has a semi-simple part and a nilpotent part. H has a semi-simple part and a nilpotent part. So the claim is that the diagrams, these two diagrams commute, where instead of G we have the semi-simple part, similarly for H, and here we have the nilpotent parts. So why is this true? Yeah, maybe I want to make sure the statement makes sense to everybody. So this, yeah, so in some sense this, we can think of this phi as intertwining. There's this word intertwiner, so that we can think of phi as intertwining H and G. And so then phi intertwines the semi-simple parts and the nilpotent parts. That's what this is saying. So what's the argument? Well, the argument is kind of nice. So first we take this phi, and we can do this with any linear map. We can factor it as as a injective linear map followed by a surjective linear map. So the first one is we map V to the direct sum of V and W, and V goes to the element that has V in its first factor and phi of V in its second factor. So this is injective just by looking at the first factor. And then here, this map is just projection onto W. So it's obviously surjective. And the composition of this is just phi, right? So now we, since phi has this, since phi intertwines G and H, we have that this diagram commutes. So yeah, this is kind of clear. Here we just do G on the V factor and H on the W factor. So we have this. So each of these squares commute, and the whole diagram commutes. And so now there's maybe this is takes a little bit of thought to convince yourself, but it's not hard to show that the semi-simple part of this is just the semi-simple part in the V factor and the semi-simple part in the H factor. So yeah, you can think about that if you're not convinced, but I'm going to take it for granted in terms of this proof. And then, because this is an injection, then we use the fact that the part 3 of the theorem we just proved to show that this diagram commutes. Because this is a surjection, we use the observation about quotients. So a surjective map is just a quotient, and that's where we use we use that argument to show that this right square commutes, and since each of these two squares commute, the whole thing commutes. And similarly for the nilpotent part. Okay, how is it? Oh, it's already past the break time. So yeah, let's take a break. I'll ask for questions when we come back, and we'll pick it up from here. Okay, let's get started again. So here's the document. So any questions about what we just discussed? All right, so this was all for, so we talked, so far we've been taking an element little g in the endomorphism algebra of a vector space. And yeah, we decomposed it into a semi-simple part and a nilpotent part. And we proved all these nice properties about the semi-simple parts and the nilpotent parts. This decomposition is unique. So there's a multiplicative version of this. So now let's take little g not to be any endomorphism, but automorphism, so something in the general linear group of V. We can, so the claim is that there exist unique elements G sub S and G sub U, such that G sub S is semi-simple, G sub U is unipotent, their product is G, and these two elements commute. And so that's the first part of the claim. So this is a multiplicative Jordan decomposition, and we have a unipotent part instead of a nilpotent part. The second part is that there are polynomials that give us GS in terms of G, G sub U in terms of G. And the third part is this nice compatibility when we have a subspace that's G stable. So first of all, it's also stable for the semi-simple and unipotent parts. And the restriction of G, the semi-simple part of the restriction of G is the restriction of the semi-simple part of G, and similarly for the unipotent part, and similarly for the induced maps on the quotient G, V mod W. Okay, so, and the proof is just kind of piggybacking on the proof for the additive Jordan decomposition. So we can take GS as before, so GS doesn't change. Now it'll have, it's semi-simple, so it'll be diagonal in a certain basis. And now all the diagonal entries have to be non-zero because it's invertible. Okay, so that's the semi-simple part. The unipotent part we get by taking the identity on V plus GS inverse times the nilpotent part. So we can think of G, so G is in GOV, but we can think of it as a usual endomorphism, and it has a nilpotent part. And now we take that nilpotent part, we multiply it by the inverse of the semi-simple part, and we add an identity. So that makes it unipotent. Adding the identity to a nilpotent operator makes it unipotent. And then you check that it has the right properties. So it's yeah, pretty straightforward given what we've seen so far. All right. Okay, so we want to extend this. So okay, so what have we done so far? We talked about the additive Jordan decomposition for endomorphisms of a vector space. Now we formulated the multiplicative Jordan decomposition for automorphisms of a vector space, so things in GLV. And we want to extend this multiplicative Jordan decomposition from GLV in two directions. So first, we want to generalize it to certain operators on infinite dimensional vector spaces. So far, V was always finite dimensional, but there's a certain infinite dimensional generalization that we'll talk about. And second, we want to generalize it in a different direction to any linear algebraic group. So right now we just consider GLV, that's a linear algebraic group, but we want to, there's a Jordan decomposition for any linear algebraic group that'll be our goal to get to that Jordan decomposition for any linear algebraic group. Okay, so first of all, what do I mean by the extension to the infinite dimensional case? So if we have a vector space that's not necessarily finite dimensional, so it could be infinite dimensional, then an automorphism of V, a linear automorphism of V, is called locally finite if V is a union of G-stable subspaces that are finite dimensional. So in terms of notation, so you can think of V as the union of W sub I is some index set, such that G preserves each of these WIs, and each of these WIs is finite dimensional. So yeah, so like to understand the action of G on V, this automorphism, it's just enough to understand some finite dimensional data. Of course, there's infinitely many vector subspaces W, but still G is just a finite thing on each W. Okay, so if we have a
example, can you give an example of such an operator?
Yeah, so an example would be where we take, so we saw an example, I guess, earlier in this lecture when I was reviewing the material from last time. So if we take V to be the affine algebra of G, so K brackets G, then we had these rho sub G's, if you remember from before. So rho sub little g, so it acts by taking a function to the new function that first multiplies on the right by G and then applies F. And we argued that each rho G is locally finite on K brackets G. And in fact, this example generalizes. So anytime we have a affine G variety X, then each element in the group defines an operator on the affine algebra K brackets X, and that operator will be locally finite. Does that make sense? Okay, great. All right.
Priori in this definition, though, we're not expecting necessarily that GL of V is a is a variety though. I mean, if it's infinite dimensional.
Yeah, exactly. So GLV is, we don't think of it as a variety. We just think of it as yeah, as a infinite dimensional space. Yeah. I guess, yeah. I mean, this definition makes sense even if we have something in end V. Yeah, so that's also fine. Okay, so yeah, so okay, so such an element, such a locally finite element. So we also say that the action of G is locally finite. That's kind of equivalent. So it's semi-simple if the restriction to any finite dimensional G-stable subspace is semi-simple. And it's locally unipotent if the restriction to any finite dimensional G-stable subspace is unipotent. So we define these properties in terms of these finite dimensional constituents that are G-stable. Okay, and so then I guess the result is that this we can extend this Jordan decomposition to operators, invertible operators in this on this infinite dimensional vector space in the following way. So so if we have a locally finite element, so this only really works with these locally finite elements. It's not really well defined for other elements. So if we have a locally finite element, then then we have this multiplicative Jordan decomposition. So there are uniquely determined elements GS and GU, and this should say, so GS is semi-simple and GU, it should say it's locally nilpotent. Let me fix that. Sorry, locally unipotent. That's the terminology. And they commute and their product is G. And these definitions are compatible with the finite dimensional definitions we gave before, in the sense that if we have a G-stable finite dimensional subspace, then the semi-simple part of the restriction is the restriction of the semi-simple part for a locally finite operator, and similarly for the unipotent operators. Right. So yeah, I mean, given what we've done before, this lemma is not really anything new. Since G is locally finite, we can write V as a union of subspaces that are finite dimensional and are stable under the action of G. And then we notice that, yeah, then if we take the restriction of G to any of these Wi's and we take the semi-simple part and further restrict that to the intersection with the Wj, then by what we argued earlier, that's the same as just restricting G directly to the intersection and then taking the semi-simple part. But then we could have switched the role of I and J. And so this is true for all I and J in our index set. And as a consequence, these restrictions, G restricted to each Wi, taking the semi-simple part, these all glue together to give a well-defined element of, well-defined automorphism of all of V. So that's the idea. And then you just check the other things from this construction.
So what do you mean by locally unipotent?
Oh, I gave the
For each
definition.
Wi?
So it means that each, the restriction to each finite dimensional G stable subspace is unipotent.
Okay, thank you.
The definition, I don't want to scroll back now, but if you just scroll back, I gave the definition of a few pages ago. All right, so that's, sure.
But this is maybe only tangentially related, but sort of relating to what I asked earlier. If you have this union of finite dimensional subspaces that makes up the whole space, could you consider the restriction to be like a variety for each of those subspaces. So it's like GLV can be considered as like a co-limit of varieties.
Exactly. Yeah. Well, not all of GLV, only the locally nilpotent part.
I'm sorry, why can't we just, what was the obstruction to?
So if you had something that does not, maybe it'll still work, but yeah, I need to think about it. I guess, yeah, maybe it still works. That's a good question though. Yeah, let me think about it and I'll tell you if I have any comments there.
Is there any, can you have in a modern language such result? Is there any shift structure here or such that you're doing?
Not here, I don't think.
Okay.
If I may remark,
Sure.
that, okay, at least finite dimensional Jordan decomposition is a specific case of the classifications of modules over PIDs. So you have the ring K of T, where T is your linear transformation. So it's a PID. And similarly to how every abelian group is a sum of cyclic modules, this K of T acts on the vector space Kn. So in a sense, in the modern language, it's just a special case of this classification theorem.
I would agree, but I think there's some. So where do you get the semi-simple and unipotent parts?
Yeah, actually, I was thinking about this during the lecture. I don't know right now. When you write it up, it's kind of clear, but I'm not sure what to say right now.
Okay. Yeah, but yeah, it does come down to these sorts of results with, like we mentioned the Chinese remainder theorem, so that's also like part of this tool that you need for this classification. So yeah, these ideas are all kind of interrelated. Yeah. Okay. Thanks for the remarks, though. Okay. Any other questions, remarks, comments? Okay. So now this gives us the generalization to infinite dimensional representations. What about to any linear algebraic group? So we've only seen this Jordan decomposition in the case of GLV. What about for an arbitrary linear algebraic group? So first of all, we go back to this row of G that we had before. So this is a K-algebra automorphism from K brackets G to K brackets G. And so this is the same thing we had before. And so, so as I mentioned, each of these row of G is locally finite. And with using the infinite dimensional Jordan decomposition, we can decompose row of G into its semi-simple part and its unipotent part. And this unipotent part really means it's a locally unipotent operator. And yeah, so, okay, so that's one thing we'll need. Another thing we'll need is the sort of the analog to this row of G for the left multiplication action of G. So in that case, this operator becomes the following. So it takes F to the composition of first multiplying on the left by G inverse and then applying F. So this is a different algebra automorphism of K brackets G. And you can prove that if we have one of these lambda sub G's and we have a row sub H for a different group element H, then they commute. So these as automorphisms of K brackets G, these commute for any G and H. Okay, so yeah, I mean, that's, you can write it out, but it's kind of clear because here we're multiplying on the left and in row of G we're multiplying on the right. So it does, you can, yeah, those two things commute. All right, so in other words, the action of G by left translations commutes with the action of G by right translations. All right, so now here's the result, the generalization to any linear algebraic group. So if we just take any element in the linear algebraic group, then there are unique elements G sub S and G sub U, such that the semi-simple part of the operator rho sub G is given just by the operator rho sub GS, and similarly for the unipotent part, and these two elements of G commute.
This is for every row, right?
For every G.
No, but
For every row sub G, yeah, for every row sub G.
Yeah, okay.
Yeah, I mean for any G, hence for any row sub G.
Okay, I see.
Also this decomposition interacts nicely with homomorphism. So if we took homomorphism of algebraic groups and we took some element G, took its image and took the semi-simple part, that's the same as, we get the same thing as if we took the semi-simple part first and then applied the homomorphism. Same statement for the unipotent part.
By two, you mean affine algebraic groups?
By, so linear algebraic group, is that what you were asking?
Linear algebraic groups, yes.
Yeah.
Do you mean by two linear? Okay.
So the term linear refers to, yeah, when the underlying variety is affine. And we showed that any such thing is actually a closed subgroup of the general linear group. So that explains the terminology linear.
Yes, but I mean in two, it's not for all algebraic groups. You just for linear algebraic groups.
That's correct, yeah.
Okay.
Yeah. Okay, and I mean, okay, I guess I've been using some of this terminology already. So G sub S is the semi-simple part of G. It's uniquely defined. G sub U is the unipotent part of G. We say that G is semi-simple if it's equal to its semi-simple part. In other words, the unipotent part is 1. And it's unipotent if the semi-simple part is 1. So then it's equal to its unipotent part. Okay, so how do we prove the theorem? So, okay, so first of all, we take this row of G and it's an algebra homomorphism. What does that mean? That means if we take some, a pair of elements in K brackets G and multiply them and then apply row G, that's the same as first applying row of G to each of them and then multiplying them together. So this diagram commutes. So this, yeah, if for any algebra homomorphism, this diagram commutes. In particular, it commutes for the algebra automorphism given by rho G. Right. So now we use this fact that I mentioned above, that if we have this sort of commutative diagram. So this means that this map M, which is a linear map, intertwines rho G tensor rho G and rho S. Rho G just one factor of rho G. And so what this means is that if we replace these maps by their semi-simple parts, we still get a commutative diagram. So we can just replace rho G by the semi-simple part of rho G.
Why what is M? Is the co-multiplication?
It's just a multiplication map.
But it's not. But what do you mean? You have a multiplication map on the groups, not on. So it should be the other way around, right?
No, not quite. So I mean, you do have a multiplication map on the groups, but this is something different. So K brackets G is an algebra. So algebra means we can multiply things together.
Okay.
Yeah. I mean, we do have the column multiplication in the other direction, but that's not relevant at the moment. Okay, so it means, so since we get a commutative diagram with rho G replaced by the semi-simple part, we get that the semi-simple part is an algebra automorphism of G. So what that means is that let's think about the following map. We take K brackets G, we take an element there. We apply this algebra automorphism given by the semi-simple part of rho G, and then we evaluate this at the identity. So this gives us a homomorphism from K brackets G to K. So basically we take the F, we do something to it, and then we evaluate at the identity. So this algebra, and as we talked about previously, any algebra homomorphism from an affine algebra, from the affine algebra of a variety to the ground field K defines a maximum ideal, which defines a point in the affine variety. So in this case, our affine variety is just G. So this homomorphism defines a point in G that we call G sub S. And this G sub S has the property that if we take any function and if we want to evaluate it at G sub S, then what we have to do is do this homomorphism. So this homomorphism amounts to evaluation at G sub S. Okay, so that's just some algebraic geometry. Okay, so yeah, hope everybody's comfortable with the fact that maximal ideals in K brackets G give us elements in G. So that's what's happening, and now we need to show that. So we remember what we're trying to show. We're trying to show that the semi-simple part of rho sub G is just rho of G semi-simple part. So we need to show that this semi-simple part is just rho of G sub S, now that we have this element G sub S. Okay, so how do we do it? So let's take an element X in G. So this is my X, sorry that...
I'm sorry to backtrack a little bit.
No problem.
I'm just a little confused in general, actually, about what the corresponding property for being, I know it's an algebra automorphism, like a K algebra automorphism, rho G. And you mentioned that rho G, that diagram before just earlier commutes because rho G is a Hopf algebra automorphism. But what is the property for being a Hopf algebra automorphism? Is it because it's like the dual of having a group algebra homomorphism, right?
Yeah.
But what does that mean? Like, do you just explain it categorically? Is it like a natural transformation of these diagrams between algebras corresponding to the algebraic groups, or is it like?
So I'm not exactly sure what you. Yeah, I'm not exactly sure what you have in mind, but homomorphism between Hopf algebras is this sort of diagram, but where you have the coproduct here. So that's the thing. Yeah, that's all it is.
So this characterizes it.
Yeah. So, rho G. I need to think for a second if it's a Hopf algebra automorphism.
That's the next question I was going to ask is, when did we show that this diagram commutes?
So this is not, there's no Hopf here. So this is just an algebra automorphism. So I guess I didn't spell it out, but it's fairly basic. So you just take F and H here, two functions, then you get some things here, and if you multiply them together, then you get the same as if you went the other way around. Yeah, I guess, yeah, it's not hard to show that this is an algebra automorphism. Yeah, in terms of whether it's a Hopf algebra automorphism, I think, I need to think about it. I kind of don't think it's a Hopf algebra automorphism, but maybe it is. Not sure if I answered your question. Does that make some sense?
Well, what does characterize a Hopf algebra? If you have a K-algebra automorphism, what would characterize it as a Hopf algebra automorphism?
It would be, yeah, you need to commute with the coproduct. So this sort of diagram, but where you have the coproduct here and here. Yeah, so a Hopf algebra, a map between Hopf algebras.
The arrows go up?
Yeah, so yeah, the arrows go up, yeah.
Okay, that was where I was confused.
Yeah, you just switch around all the arrows. I mean, these arrows still go this way.
Oh, multiplication, like you take each tensor, like A tensor B, and you make it AB.
Exactly, yeah.
Okay, I was a little bit.
Oh, no problem. I get confused about these things all the time. Yeah, that's all that's going on here. Okay, any other questions? Everybody clear on how we got this element G sub S? I think that's kind of the key idea of this proof. The rest is kind of straightforward.
Did you explain the line above, line 4? No, after. The line after, why FGS is equal to this? Because I didn't understand.
Yeah, so that's kind of by this choice. So the idea is that any algebra homomorphism from the affine so you forget that this is a group, this is just some variety, some affine variety, K, and we have its affine algebra, and we have a homomorphism to the ground field K, right? So there's some affine variety and some algebra homomorphism to the ground field K. So now the kind of the philosophical statement is that any such homomorphism has to be given by evaluation at a point in this affine variety. Why is that? Well, because the kernel is going to be a maximal ideal. And we already argued that maximal ideals correspond to points in the affine variety. Maximal ideals in the affine algebra correspond to points in the variety. And so now here we have some complicated thing that's just an algebra homomorphism. So it has to be given by evaluation at a point, and we call that point G sub S.
Wait, what is the relation between the two parts? You said that the kernel is maximal, I agree, and you say that this map have to be evaluation. Why and how does it related to the same GS as the kernel?
Yeah, okay, so I think so the reason why comes down to algebraic geometry that we kind of reviewed. So I'm not sure if I want to go into too much more detail than what I said, but it's just a property of affine algebraic variety. So I guess it goes back to like the Nullstellen Satz that the maximal ideals of the polynomial algebra are just given by evaluation. They're just given by the points in the vector space of the appropriate dimension. And you just start with that fact, and using that you build these affine varieties, and you see that the maximal ideals correspond to points, and these homomorphisms are just evaluations. Yeah, so it's an important point. I guess I'm glad you asked, but maybe I don't want to backtrack too much into that sort of algebraic geometry. Maybe you can take a look back at chapter 1 and then let me know if you have questions. And G of S is just what we're calling this point. So we know that there's some maximal ideal here. That's the kernel, and that corresponds to a point in G, and we're just going to call that point G sub S. Does that help a little bit?
Yes, thank you.
Okay. Okay, so how does this, so remember we're trying to show that this is just rho sub G sub S. So how does it work? Well, we need to show that they match on all F, and to show that they match on all F, we need to show that they match for every F, they match on all X. So we take X and G, and we evaluate this at X. That's the same. So now we use this lambda here. That's the same as if we did lambda of X inverse and evaluated at the identity. So this is just a definition of what these lambdas are doing. And now lambda commutes with rho G. So that means that lambda commutes with the semi-simple part. So we can arrange it in this way. Yeah, I guess I said that here. So then now, okay, so now we think of lambda of X inverse applied to F. We think of it as one thing, as one element in K brackets G. And we're applying this rho G sub S to that one thing. That's what's happening here. And by definition of G sub S, this means we're evaluating this lambda X inverse of F at the element G of S, G sub S. What does that mean? Now let's use lambda again. Let's expand out the definition of lambda. That means we're just multiplying on the left by X, and then doing multiplying G sub S on the left by X, then applying F. But then that's just a definition of doing rho sub G sub S of F and applying it to X. So yeah, so that's, and so since this is true for all X and then for all F, we get that these two automorphisms of K brackets G are the same. Yeah, so yeah, this is probably kind of confusing, but I think if you sit down and maybe at your own pace, work through what all these automorphisms are and work through the definitions, it's pretty straightforward. It's just manipulation of symbols. Okay, and so similarly, we obtain an element G sub U, and we show that the semi-simple part of rho sub G is just rho G sub U. And yeah, and okay, I think I'll kind of skip this computation, but you can also think about why they commute, and it amounts to the fact that these two automorphisms commute. So if we take, yeah, I'll just let you read through this, and yeah. All right, so then we have the second part, and I think rather than going through the second part, I think I'll stop the lecture here, and I'll ask if anybody has questions. Also questions on last week's material, since I know there was no TA session this week. But yeah, so let me just say one word to wrap up what we did. So far we found these elements. We talked about the additive Jordan decomposition and then the multiplicative one. We showed an extension of the multiplicative Jordan decomposition to an infinite dimensional setting. And now we're discussing the generalization to any linear algebraic group, not just the general linear group. Okay, so any questions about anything?
I just wanted to mention before my question. I understand finally understand what you said, but did you actually use I understand why each homomorphism to the field from the variety is evaluation, and also the relation to the kernel, why it is the same. by Null-Stahlen-Salz. But
Mhm.
did you actually use the fact about the kernel, or you just say it is evaluation at the point, pick that point? You didn't use anything about the kernel, right?
Nothing specific about the kernel, no.
Okay, thank you.
Yeah, just the fact that it's the maximal ideal.
Why? How did you use it? How did you use it, say maximal ideal? Only you
Because-
said it evaluation at the point, right?
Yeah, so any maximal ideal is the kernel of evaluation at some point.
Okay.
Yeah.
Okay.
Yeah, but there's nothing special. I mean, yeah, we didn't need to prove anything specific about the kernel. We just needed to know that it's a maximal ideal.
Okay, thank you.
Mhm. Any other questions?
So you proved uniqueness in the case of the additive Jordan decomposition, but here we're starting with the multiplicative form of it, and
Mhm.
I don't see how is uniqueness immediately follow an analogous way from the additive form, or
Yeah, it pretty much, yeah, it does. So are you asking about, so let me scroll back up
do
here.
you just like subtract one from the unipotent element, and then show that must be the same as any other?
Oh, I see what you mean. I think it comes down to the fact that if something is both semi-simple and unipotent, then it must be the identity. Yeah, so the semi-simple part, so for showing, so if we had a different multiplicative Jordan decomposition, then the argument for showing the semi-simple parts are the same is the same as in the additive case. You'll agree, right? And then for the unipotent parts, yeah, I think maybe you do need a small argument, sort of like, yeah, to show that the difference of commuting unipotent elements is again unipotent. Yeah, you probably need something like that. And then that gives you uniqueness. Yeah, that's a good point. Yeah, I think you can do that. Maybe there's some way to get around it, but yeah, that's a good point.
I have a question about the homework, about the week 2 homework.
Sure, yeah.
About the first obligatory question, I didn't knew it was about SL2. I didn't knew. I think I succeeded to almost succeeded to finish the question, but my only thing that I didn't knew is how to manage the kernel. What can you say about the kernel given Hopf algebra homomorphism?
So can you remind me what the question was?
Wait, yes.
So it was an exercise in Springer, right?
Yes, 215. 215.
215. Yeah.
Part 3.
Part 3, yeah. Okay.
Yes, so I think that I managed almost everything in this exercise. The only thing that I didn't know how to solve up is how to say something about the kernel. Like you say in A, they ask you to prove that the kernel has order at most 2. And in C, they ask you to prove basically that the kernel is 0. So those two things I didn't succeed. How to manage kernel given a half algebra.
Right. So, okay, so we have, so the kernel is, yeah, so it's, the kernel refers to the kernel between the kernel of this map between the algebraic groups, right?
Is it the same? Is it has correspondence? Has it any
Oh
correspondence?
yeah, so what, so first step is what is it in terms of the algebra homomorphism? Right, that's the first step.
Basically, the homomorphism is the injection. It's just the embedding. So
Right. So then the kernel will be
0. But I thought about the co-kernel, but I didn't know how to
So
prove it.
the kernel, yeah, the co-kernel. So yeah, so that's I guess what. So what we want is we want to talk about, okay, so we want to know about the kernel of this group homomorphism. So that's the inverse image of the identity, right? So to talk about the inverse image of the identity, like we were saying before, that corresponds to a maximal ideal, in this case in B. And so what we want to do is the kernel will be the tensor product of A over B with this maximal ideal corresponding to the identity element in PSL2.
How can you see this? I didn't know how to prove such things. And
yeah, okay, so it's, yeah, I mean, I guess it just takes some.
Okay,
well,
another time.
It's just the fiber product over a point. We saw this in say the coarse category theory. So the fiber product over the point is, if you look at it at the level of the algebras, it's going to be the tensor product that Jordan Ganef mentioned, and the fiber product of the point is you can comprehend it as the fiber of the
how. Even so, how can you prove that it corresponds to the dualism between the categories and such? How can you?
Yeah, like Benjamin was saying, it comes down to what we were talking about with products, like the product. So the fiber is a fiber product, and products correspond to tensor products of the algebras. And the fact that the kernel is at order at most 2 corresponds to showing that this tensor product as a vector space is of dimension at most 2.
Yeah. Maybe this somehow, it at least intuitively, maybe I'm wrong, but because B is generated by things of degree 2, maybe you can even say that all of the fibers are of order at most 2 or something like this. I don't know.
Yeah.
Maybe, I'm not sure. Similarly to how you project a parabola, and the fibers are at most 2 because kind of the map is of degree 2. I don't know. So maybe.
Yeah, I mean, since it's a map of algebraic groups, all the fibers will be the same.
Okay, yes, it's homogeneous.
Yeah.
Sure. Yeah, that's a good point. Yeah.
Okay, thank you. So first, what you told me, that the kernel here on the right, the kernel on the right is just the fiber product between PSL2 and 0 with respect to SL2. So because it's essentially the dual category, so it corresponded to A, if I'm, let me say it correctly, B tensor and P tensor 0 with respect to A. Or A, oh no.
So it's the tensor product of A as a B module with the kernel also as a B module over B.
Yeah, something like this.
Okay, so it was wrong. The right side
Yeah,
is
yeah,
the two product and fiber product with 0.
I think you said it.
Spectacent,
You
yes.
said it.
I said the co-product
Yeah.
before. It was wrong.
Yeah.
I said okay.
Yeah. Yeah.
So this is how you show this, and you can conclude by this that this is just the core kernel.
Yeah. It's. I'm hesitant to use the word co-kernel, but yeah, I think categorically it's the co-kernel. Yeah.
Because they is it okay to say that they are essentially dual to each other as category in linear?
Yeah.
Okay, thank you.
In fact, like the hop. So on the one hand, we have linear algebraic groups. On the other hand, we have affine hop algebras. Yeah.
So you can say the co-kernel because it's dual. Okay.
Yeah, you can. Yeah, you can.
Thank you.
Mm-hmm.
Okay, also, my question, just the case where the kernel is of order 1, it's not like there is, it's not as if there is a ramification. Just the tensor product you mentioned will be of dimension 1. There can't be, these maps can't have ramifications, right? Homomorphisms between algebraic groups.
Yeah, in this setting, because there's no nilpotent elements. Everything is just varieties. There are no schemes.
Yeah, sure. I mean, but still, you can still look at it as varieties and see that there is ramification. I mean, right? In a sense, like for example, it's local. For example, you take the parabola and you project it, so you will have this ramification, and it's a local thing. You will see it. So, but I'm not sure how to phrase it, but for algebraic groups, kind of how you said, all the fibers should be the same, and the generic fiber probably is like good. I don't know. So it's not. I mean, if there are two cases here where the kernel is of order 2 and of order 1, and what this means that in the order 1 case, that really that vector space is of dimension 1, not as if it's of dimension 2, but we still see 1 point somehow, right?
Oh, I think I see what you mean. Yeah. Yeah, because, okay, if these were not groups, we could have like a cone point or some singularity. Yeah, okay, I see what you mean. But yeah, since these are maps of groups, everything is kind of homogeneous. All the fibers are the same, so that
it must be
happen.
a regular map in the sense that the differential is onto or something. It's just a homomorphism between groups.
Yeah. I always get confused about the terminology.
What is regular? It's strange, but I mean the differential would have maximal rank at each point or something like this of a homomorphism between algebraic groups.
Not necessarily, I don't think.
Not necessarily.
No, because you could have. I mean, if it's an injection or a surjection, yeah, I think so. Yeah, then I think it's true, but it could be like if it has some non-trivial kernel or co-kernel, then it will be then you can factor it non-trivially as a quotient followed by an inclusion, and each of those two maps will be. The differential will have full rank at all points, but the composition, I don't think it will be true for the composition.
Okay.
Yeah.
I should think about this, but okay, thank you.
No problem. So just one question. So I guess there's a lot of people who are also in the category theory course, right? In this.
I actually don't know. Tal is there.
Okay.
Tal is there.
Okay. Yeah, it's. I think this class and the category theory class could kind of complement each other quite well. There's a lot of.
Yeah, but I think the audience here knows quite well categories.
Oh, okay, great.
Or at least, I mean, it's just by my guess. I don't know everyone, but some of the names I see, I think they're advanced students.
Okay, great. Then I can slip in a bit of more category theory.
Great. Okay.
Yeah. Okay.
Goodbye.
Thanks a lot.